Okay, welcome to the fourth lecture, which is treatment planning for radiosurgery. What I want to do today is go over some of the basics of treatment planning from one of the possible ways of doing it. There are multiple ways of doing planning and treating radiosurgery lesions. At the University of Florida, we have used a technique called sphere packing, and that's what we're going to talk about today. There are numerous reasons why we use this, and I'll try to explain that as we go through. Talk about the difference between radiosurgery and radiotherapy today. Talk about the criteria for a good plan, the scoring, techniques are available, how you do sphere packing, tools, and then Dr. Friedman and I will go into a example session where we actually do a bunch of planning for you live. I'm going to go through this rather rapidly today. There will be 2 lectures on the website. Today's abbreviated lecture, and then a much longer lecture that actually goes into a lot of this in much more detail. Okay, radiosurgery versus radiotherapy. If you actually go to the radiation therapy conferences and you talk to radiation oncologists, this diagram explains kind of what they think about as they do planning. They have something called a gross target volume. They have something called a clinical target volume. They have something called a planning target volume. And these are all nested structures which lead them to larger and larger treatment volumes based upon different criteria, what they can see, where they know there's subclinical disease, and then adding an uncertainty into the overall treatment because of the fractionation scheme and the day-to-day setups. Radiosurgery is very different than this. In radiosurgery, we have what they would refer to as the gross target volume, what you can see on the scan, what's actually there, and we treat that very conformally, and we don't treat anything else. The other big difference that we're going to talk about between radiosurgery and radiotherapy is the fact that we treat very concentrated disease, and we'll talk about that in a moment. The radiation oncology literature always has this diagram, and it's a diagram that shows the percent of the target versus dose that is cured or affected by the treatment. So you get to very low doses, hardly any effect. As you get more and more, you head up on the sigmoid curve, and eventually you plateau off where you've given sufficient dose that you get no more therapeutic effect. Shifted to this curve, and hopefully shifted to the right, is a following curve which is giving you the complications. And so as you give more dose, hopefully what you can do is you can get up on the shoulder of this cure curve before this complication curve takes off on you. And if you can, then you've got a therapeutic window that you could actually exploit. If these curves are very close, and by the time you get up on this control curve, you're up high in this complication curve, then you've got a real problem. These curves are utilized in radiation oncology in 2 ways. One is, as we will do in radiosurgery, which is keeping dose off of non-target structures, and the other one is by sublethal repair. And that's shown in this slide. So the way radiation oncology has evolved is that if you give cells a dose of radiation, you will go ahead and have, for every increasing dose, more and more cell death. If you actually give a small dose and wait a period of time, cells repair. And what you see here is the repair. And so I've given it 1 dose, they repair, a 2nd dose, they repair, a 3rd dose. And so if I look at the single dose versus the multi-dose has less of an effect because the cells, after each fraction, have the ability to repair the DNA damage. The key to fractionated therapy is that the DNA damage repair for normal tissue is better than it is for tumor tissues. Tumor tissues have less of ability to repair this sublethal damage. So what happens over and over again is that you keep on separating out the normal tissue and the tumor tissue, and by the end of multiple fractions, whether it's 10, 20, 30 fractions of therapy, you get a differentiation between the overall effect of the normal tissue and the overall effect of the tumor tissue. In radiosurgery, we do not use this radiobiological principle at all. What we use simply is the overall single fraction effect. Okay, so what we're going to talk about today is sphere packing. And in sphere packing, as Dr. Friedman showed in his previous lecture, you could do it a bunch of different ways. The Gamma knife is probably the device which is used on the most patients in the world. Linear accelerators, also by using multiple arcs of radiation, could also create spheres of dose. And so by these two techniques, you could actually create very dense spheres of radiation dose, and you can use these spheres of dose placed over target tissues to treat the targets. Okay. I want to just go into a moment of nomenclature, because there are certain concepts and certain issues that you don't deal with in surgical training. So I just want to talk a little bit for a moment about a radiation beam. So if we have a patient, and we have the patient inside of a calculation grid, and what you see here is just a grid overlaid, so I have some spatial registration, and I have a radiation beam coming into the patient. What I could do is I can calculate the effect or the intensity of this radiation beam as it goes to the patient. And what you see here is another rendition of that. I've got the patient here, and the radiation beam goes in, and there are different intensities. The radiation beam is more intense in the middle, less intense at the edges, slightly less intense as it comes into the patient. It takes a little bit of time for it to build up its intensity, and then you get this high dose of radiation. What we normally look at are not these numbers. What we look at are what we refer to as isodose curves, which are curves connecting these common points of dose. So what I've done here is I've just produced an isodose region of the high intensity. So when you see an isodose curve, it basically is a curve connecting the edges of a volume which have similar doses. Okay. When I look at an isodose curve, what I see is this rendition down below, which is the fact that I've got a radiation beam, and if I look at it in 3D, this radiation beam over the plateau of background dose gives you a bump or a region of volume of radiation intensity. And what this representation does is it tells me that the intensity of the beam over the central region is relatively flat, and then it tapers off very rapidly. So when we look at isodose curves, we look at distributions, what we're really looking at is a cut through this intensity plane of the radiation beam. Okay? And we refer to this as if we look at the intensity, if we just look at the envelope of this, we refer to this as a cross plot. So a cross plot is going through this distribution at a particular level and then just mapping out what the intensity is. Okay? And it looks like this. And we'll see these cross plots in the lecture today. And here's one on the lower right. You see there's a radiation distribution. It's not on any particular anatomy. It's just shown there inside the patient's head. And what we have below it is a cross plot showing the intensity of this radiation beam as we traverse and we look at the doses through the patient from left to right, right to left. Okay? Again, the cross plot, the distribution, all showing us the same thing. Okay. Now, if I have a distribution like this and I have a target, the question is, where do I place the target? At what point do I try to get the target so that the target is covered by this width of this distribution, or do I use a wider width of the distribution? In other words, if I have a target that's something on the order of 14 millimeters in diameter, do I use a collimator that's kind of 14 millimeters up at this upper region, or do I use a 10 millimeter collimator that allows me to cover it down at a lower intensity level? And what you see in right and left are those two examples. And just to take away some of those nested curves, what I have on the left is a 14 millimeter collimator shown on a 14 millimeter target, and on the right is a 10 millimeter collimator shown on a 14 millimeter target. If you look at them, they look, aside from the fact that I had to blow one up a little bit more because it's a smaller scan, they really look almost the same. The target coverage is very close. What is not close is the second line, and the second line shows you the half dose of the target. So what I've shown on the left side is targeting the distribution. Let's say we give 2,000 centigrade to this lesion, and what the blue line is the 1,000 centigrade line. On the right side is the 2,000 centigrade line and a and the 1,000 centigrade line. And it turns out that the 1,000 centigrade line is much broader on the right than it is on the left. The reason for this is that when we actually prescribe a dose in radiosurgery, what we try to do is we try to prescribe a dose so that the difference between the target and the non-target tissues is falling off as rapidly as possible. We want to protect the target, we want to protect the non-target tissues, the normal tissues. And the way we protect these normal tissues is by looking at that cross plot and picking a point on the cross plot which gives us the maximum rate of change between the dose we select to give the target and the dose to half target. And so on this cross plot, if for example we selected the 95% intensity level, then what would happen is we go 95 to 47.5, and that takes 5.7 millimeters to drop that dose. And that's just the physics of the situation. There's not much we could do about that. If I choose the 80% intensity level, what happens is I can go from 80% to 40% because I'm off this plateau. I'm now on the steep part of the curve. I could drop it off much more rapidly. And so what this means is if I select the right collimator and I get the kind of 80%-ish range to actually sit over the edge of the target, I'll fall off to the minimum dose much more rapidly because I'm prescribing on the edge of this target. This next slide just shows you what happens if we choose the 95, the 90, the 80, and the 70. And it shows at 95 it took me 5.7 millimeters to drop off to that dose to half dose. 90 it took 4.5, at 80 3.8, at 70 3.9. Started going up again because I'm on the steep part of the curve, but I'm picking up this other plateau on the other end. So what the take-home message is that there is kind of what you refer to as an optimum point, a sweet spot in these dose distributions that allows you to pick a dose so that the target dose to half target dose shell, that shell of fall off is minimized, and that's really what you want to try to do. The reason why we do sphere packing is that as you look at the next couple of slides, you realize that these spheres of dose have this nice intensity profile, this nice property. And if I align my spheres of dose with the edge of the target, I am guaranteed to have this steep dose gradient at my interface between my target and my non-target or my normal tissues. And that's very important. It turns out in some of the other techniques, while you can do that, it's a lot easier to actually not optimize. And so we've stayed with sphere packing over the years because it turns out that it's a technique that if you actually practice it properly, and we have some tools that we'll show you today that allow us to do that, you can go ahead and get this steep dose gradient at that interface every time. Okay. Just another example, just to drive this point home and drive it into the ground. I have a patient, same target. I just split the scan left and right, and on the right side you see a dose distribution which falls off very rapidly. On the left side, I've created a dose distribution by not following the rules that I need to follow to create these spheres. I've created an inferior distribution that falls off less rapidly. And if I do that, then what happens is, again, I wind up with it taking longer to get down from my target dose to my non-target dose, and these tissues out here are getting substantially more dose than they are on this side with the good dose gradient. Okay. The reason why this matters is that if you look at the gradient, here's a graph showing what happens as I increase collimator size. The geometry dictates that I wind up increasing this volume that this shell takes up. And if I actually have an inferior gradient, that volume goes up much more rapidly and much higher, so that at any given target size, I'm treating substantially more normal tissue. All right, so how do we create spheres of dose, and how do we actually do sphere packing? Well, what I have here is just a circle. So this is physics, right? You need a patient, we make a circle. You need a cow, we make a circle. So here's a circle, and what I have is a radiation beam coming in from the top. Intensity goes down exponentially as the radiation penetrates through the patient. It's an E to the minus mu x absorption. There's some scatter radiation that perturbs that from a pure E to the minus mu x, but for these small beams, it pretty much is an exponential decay. And so what happens is if I have a single beam, I put it in, and if my target is here, I'm getting 78% of my dose onto the target. Well, if I want to give a dose to a target and it's inside the patient's head, getting 78%, 3/4 of the dose at the target means I'm going to have a lot more dose in normal tissue. So if I actually now take a second beam of radiation and crisscross it over the target area, I now have 156% at the target. So before I had 1.4 times the dose at the entrance as I did at the target, but now I only have 2/3 the dose because I'm bringing in the radiation beam from two directions. It's a simple overlaying mathematical averaging technique. If I continue this and I take 1 beam, 2 beams, 4 beams, 8 beams, 100 beams, what happens is this crisscrossing keeps on overlapping all of these beams on the target. I wind up with this kind of distribution which has this really high dose because of all these geometric overlapping, and then it falls off very rapidly because all of these beams diverge. It's pure geometry, nothing to do with physics. It's just pure geometry of beam averaging. The way we accomplish this in linear accelerators is that we actually arc the beam, we spread those entrance doses over the 2 pi of the patient's head, and by spreading those beams out, we get to actually practice this and get these very, very high doses and then get these very rapid fall-offs. In order to do this, you have to use a lot of radiation beams. We have to cover about 500 degrees of arcing head separation. And you'll see that when we do the plans. We have these standard 5-arc plans that use 100 degrees per arc over 5 arcs of radiation. So you need somewhere in the 450 to 500 degrees of arcing over the patient's head to get enough of these beams in to create this very, very steep distribution. Okay. If we look at what happens if we don't use enough arcs. So here's an arcing plane where I didn't use enough arcs. I just used kind of one arcing plane, and I didn't use a bunch of non-coplanar beams. I can get good target coverage, but again, that half target dose is spread out. That's not good. Over here, same distribution, same patient, I just use more arcs. It pulls that in because I now have a lot more beams intersecting, a lot more beams averaging in. I get to spread out that dose and actually move it around. And that really helps. Okay. This just shows you how we actually do this. Here's an arcing plane. We arc the patient. Then we rotate the patient because we can't rotate the machine very well except in one plane. And so by moving the patient into multiple arcs, we go ahead and actually spread these entrance doses around the patient. And the way we look at this on the computer screens is by looking at various arcing planes. Each of these represents a plane going from the front of the patient to the back of the patient in parasagittal and transaxial planes. And you get these nice tight distributions with these nice tight gradients. Because we are very, very close to using a symmetric set about the patient's head, we tend to get round distributions. Not quite round. And you can see this is not quite round, but it's very, very close. Okay, just again. Now, if I look at this, I can do some things to these distributions to get myself into a non-round. And I do that in certain situations. You'll see that in some of the examples today. If, for example, I need to spare tissues and I have these beams coming in from all over, if I eliminate the beams from certain regions, what happens is I wind up decreasing the dose in those regions. There's no beams coming in. This is pure. You eliminate the beam, you get less dose there. And so I can spare tissues by removing some of these arcing planes. The penalty for that is that I have less arcing planes to average out, and I spread the dose in other planes. And that's at times beneficial. If I'm doing a pituitary treatment, I may decide to actually eliminate some of the planes so that I actually stay off of the chiasm better. And so there are these abilities in the planning systems to go ahead and remove some of the beams. And we'll do that, and you'll see how that works. Okay? Here's an example of just removing the beams to stay off of lateral structures. Okay? When we have non-spherical and distributions that need to be non-elliptical, as you've just seen. As Dr. Friedman explained in the previous lecture, we use a technique called sphere packing. And we have a target, and we take the biggest sphere, plug it in, next biggest, next biggest, next biggest, until we get the overall thing covered. Okay? When we do that, there's one caveat that you have to remember, is that, now remember I said what we really want to do is prescribe the 80% isodose line, because to get that nice fall off. When we actually take one beam and another beam and we combine them, there's a small overlap area. And when we get that overlap area, we tend to get a small hot spot in the distribution. It doesn't bother us because it's usually buried inside of the target. And so you either sterilize the cells in the target once or twice, doesn't really matter too much, and we're able to get away with that. But what happens in that normalization is these curves are shifted, and you'll see that when we actually go to multiple isocenters, we go to the 70% isodose line for prescription. But it's really the same as the 80. It's just a normalization issue because we have the computer set to always find the maximum dose in the patient, normalize it to maximum dose. And we do that because we don't want to be fooled. We don't want to actually put a bunch of beams in and say, oh, I'm giving it the 80% isodose line. Then we find out that there's 130% someplace. So we've set our computer systems so that it always, 100% is always maximum. And when we say 80, we know that's 80 relative to 100, not 80 relative to 120. But in that scenario, we have to actually switch our normalization down to the 70% line because of that issue. Okay. Example, what you'll see us doing is doing these sphere packings, and this just shows you graphically. If we take this distribution and we take two of them, and if we don't have them close enough together, we get a cold spot. So if we're trying to cover a target, we don't want a cold spot in the middle. As we move them closer and closer together, we get a point where we actually get a nice maximum volume. It's about as homogeneous as we can get. We get that small hot spot, things look good. But if we keep moving them closer together, that hot spot gets too hot, the distributions start to actually then shrink. So there's a point where the maximum volume occurs, and that tends to be about at the nominal radius of the spheres that we pack, plus about 1 millimeter. So if you have a 14 millimeter sphere and a 10 millimeter sphere, that's 7 and 5, that's 12. If you put the two isocenters about 13 millimeters apart, you tend to be at this maximum sweet spot in the distribution. Okay. You'll see us do some planning, and these are the tools. And we're going to go through these, so I'm not going to talk about them much. We have to be able to put those distributions where we want to. We have to be able to move them apart if we need to get that spacing right. And we need to be able to weight the distributions so that we actually get the proper intensity of one relative to the other. And this is just the first sphere. Looking at it, the second sphere going in, what those distributions look like. And then a weighting tool allows us to re-weight things and to get the distribution. And we'll do this in real time in a moment. Again, that screen just showing the tools. The system you're going to see today is our in-house system. It's a system we developed at the University of Florida and one we use for day-to-day planning. There's a commercial version of this that we actually have down in the lab. And so if you're not here, there is another version of this. And we use that version to check our plans on a daily basis because that is the FDA kind of version that we rely on. They give us the same answer. You can create very, very complex distributions. And here we've just shown that we can create, we were going to write UF in the phantom. And this just shows two things. One is it shows that we can create very, very high doses of radiation. This is 10 millimeters, so the distance between the dose and half dose is again about 3 millimeters, about our standard. And the other thing it shows is that this is the planned dose, and then we actually took a sphere of something called a radiochromic a gel that allows us to expose it and then develop it and figure out where we actually deposit the dose. And what we do is we took a sphere, a flask full of that gel, we planned it, we irradiated it, we then fused it back, and this shows the agreement between what we can plan and what we can actually measure. And the agreement is very, very high. So as Dr. Friedman showed the other day, when we're doing something like trigeminal neuralgia, we're delivering 9,000 centigrade to the center of the nerve, we know we can hit it. Okay. We also have an automatic system you're going to see today. It's very quickly with system tiles. It uses something called a grass fire technique, and just go through it. We have to contour the target. Computer needs to know where the target is. We create a bunch of little voxels of the target. And then the system basically peels it apart, figures out where the middle is, uses some artificial intelligence, puts the dose distribution there just like we would normally, takes that out, redoes it again, and keeps on going over and over again until it fills these targets with the proper spheres. And here just shows that target being filled with the spheres in order to conformal distribution. If this is the target, the system would put 3 spheres in, give us a nice dose distribution that looks like that. Okay, another target. Okay, we will start often with a 9-arc set. I remember I said we use about 500 degrees of arc. When we use a 9-arc set, we do that because it's just easier to start with 9 and eliminate sometimes than it is to start with 5 and rearrange. So our normal sphere packing set is 5 arcs using about 500 degrees, and we'll use a 9-arc set when we want to eliminate things. So you'll see us do that with the planning system. So in conclusion, radiosurgery is a single fraction radiation technique. Does not rely on differential repair of normal target tissues. Radiosurgery dose distributions are highly conformal, have very steep dose gradients, are prescribed as to minimize the dose of normal tissue, and to achieve a slight misspelled dose requirements, must use non-conformal beams spread across the entrance surface. That's just in there so Dr. Friedman knows I really did make these slides myself. That concludes it, except for one more slide. I forgot. Let me just say that one of the things that our system does, and we talked about this the other day when we talked about imaging, is at the end of a plan, it prints out the checklist. And we take this checklist and we use this checklist. 4 versions of this checklist get printed out. I get one version. Each of the therapists I'm working with down in radiation oncology gets a version of it. And then Dr. Rajon Didier gets a version of it. And the system has a triple-blind check built into it. You follow the system. I set one thing. The tech sets something else. The system checks itself to make sure they're the same. And then Dr. Rajon checks both of us to make sure we've all set things properly. So we use a very elaborate system. We don't deviate from these checklists because anybody who's an airline as a pilot knows that if you deviate from these checklists, it's just a matter of when you make the mistake, not if. And so we use a very, very strict checklist system. Okay? Thank you. Now from that, I think I will switch over and start doing the demo.